The overall goal of this procedure is to determine the effect of the variation of blood hematocrit, and therefore blood viscosity, on the volumetric efficiency of a peristaltic pump. This is accomplished by first building the apparatus needed to conduct the experiment. The second step is to mix the glycerol and water solutions corresponding with the chosen blood hematocrit viscosities. Next, the peristaltic pump or syringe pump is attached to the piping of the apparatus, and the glycerol solutions run through. Since a syringe pump has a volumetric efficiency of 100%, it is used to provide reference data. The final step is measuring the head and flow rate values and recording them for each speed and dilution. Ultimately, the method of testing blood mimicking fluids of different viscosities through two types of positive displacement pumps is used to show the effect of blood viscosity on the volumetric efficiency of a peristaltic pump. This method can help answer key questions in the field of hemodialysis research, such as the effect of blood properties on the pumping portion of the hemodialysis circuit, particularly because blood could become concentrated during hemodialysis, thus varying blood viscosity.
The implications of this technique extend toward therapy of patients with kidney dysfunction. For a given hematocrit, safe values for pressure and flow rate for an optimal volumetric efficiency can be mapped to the hematocrit and implemented to ensure patient stability.
Though this method can provide insight into hemodialysis, it can also be applied in the field of pump performance research, more specifically characterizing pump performance in other industries such as the chemical industry, since peristaltic pumps are able to work with aggressive fluids and fluids with a high volume of solids.
A syringe pump moves a working fluid by pushing a stopper of a syringe at a designated flow rate. The syringe pump was used as an ideal pump because of its 100% volumetric efficiency. This allowed us to calculate the volumetric efficiency of the peristaltic pump by comparing it to the results of the syringe pump. The peristaltic pump uses a roller which is external to a compliant tube. The rotation of the roller squeezes a tube in the direction of flow, forcing fluid movement to the outlet. Because these two pumps have different operating mechanisms, it is not easy to predict which pump will give a higher head for a given flow rate. First step is to assemble the experimental apparatus with the lengths and diameters of tubing shown in the diagram. Connect the 30 cm long tube to the inlet of the peristaltic pump and the 15 cm long tube between the outlet of the pump and one side of the three-way stopper. Then, connect the 18.5 cm long tube to the other side of the three-way stopper and the 10 cm long tube to the top of the three-way stopper. Tape the 10 cm long tube and a scale with 1 mm precision, for example a ruler, to the stand. Put the inlet tubing into the 500 ml inlet beaker and tape the outlet tubing to the 250 ml outlet beaker. Next, verify the apparatus assembly by running water through it with the peristaltic pump and fix any leakages that occur. Once the system is leak-free, begin preparing the first glycerol sample. Using a mass scale, prepare 100 grams of dilution 1, the most concentrated solution, listed in Table 1 using glycerol, water, and food coloring. It is important to note that these glycerol dilutions have been designed to mimic blood at 20 degrees Celsius, which is close to the measured temperature of the laboratory room. The viscosities used in this experiment fall between the range of 4 centipoise to 25 centipoise, which has been seen in literature to be typical blood viscosities after 3 hours of hemodialysis. Mix the sample thoroughly.
Begin the experiment using only water in the inlet beaker. Measure inlet fluid temperature. Run the sample through the peristaltic pump at speed settings 2, 6, 8, and 10. When the pump head settles at each speed, usually around 1 minute after starting the pump, record it using the scale attached to the side of the apparatus. This measurement is the experimental head. At each speed setting, measure the flow rate. Start the stopwatch when the volume in the outlet beaker reaches the 50 milliliter mark, the lowest line on the inlet beaker, and stop it at 30 seconds at the same time as turning off the pump. Measure the change in volume of the sample in the outlet beaker after 30 seconds. The volumetric flow rate can then be calculated by dividing this volume change by the elapsed time. Repeat the measurements 2 more times with the peristaltic pump. Place the syringe in the syringe pump and lock it into place. Note that the system piping remains the same, with a part of the piping being squished by the rotor of the peristaltic pump. Run the sample at the flow rates calculated for each of the 3 runs for each speed setting. When the pump head settles at each flow rate, use the scale attached to the side of the apparatus to measure and record the head. Repeat the measurements 2 more times with the syringe pump.
After the water trials are done, repeat the previous procedure using the prepared glycerol solution. Once complete, remeasure the sample mass and dilute the sample to the next dilution. Repeat the procedure for dilutions 3 and 4.
If we were to consider all of our data, the p-values range from 0.04% to 3.85%, meaning that our data is accurate with higher than 95% confidence. Shown here is the graph of the peristaltic pump head versus the average volumetric flow rate for samples of 5 different viscosities. First, we have blue data points which represent trials done with water having the lowest viscosity. Then, we have the glycerol dilutions and increasing glycerol weight percent. Green at 45.2%, orange at 48.9%, yellow at 54%, and red at 60%. Each experiment was repeated 3 times, in other words, the average of the 3 points was taken at each flow rate.
Also, the error bars are all represented by standard deviations.
Since the error bars for the 3 lowest viscosities are superimposed, the data for these 3 viscosities are deemed to be insignificant despite our level of confidence in the accuracy of the data. However, the error bars for the 2 highest viscosities do not overlap, meaning that the data for these 2 viscosities are significant. For both of the thickest dilutions, the average pump head increases linearly with increasing average flow rate. At given flow rate, the pump head is higher for the thicker dilution than for the 54.1 weight percentage glycerol dilution. Also, the largest increase in pump head for a change in flow rate occurs with the thickest dilution, which may be attributed to the decreasing efficiency of a more viscous working fluid. More energy is required to move the fluid, evident by a larger change in head values. Here, we see the graph comparing the head versus flow rate for the peristaltic pump in blue and the syringe pump in orange. There are large deviations in both the flow rate and pump head. Therefore, the data here are insignificant. The same is also true for all glycerol dilutions except the thickest one.
The head flow rate graph for the thickest dilution shows non-overlapping error bars which indicate significant data. For both the peristaltic and syringe pumps, the average head increases linearly with increasing average flow rate. In this case, the peristaltic pump provides a higher head for a given flow rate than the syringe pump. For our experiment, volumetric efficiency is calculated as the experimental volume flow rate divided by the reference volume flow rate times 100%. At a given head, the experimental flow rate is that provided by the peristaltic pump, whereas the reference flow rate is that provided by the syringe pump. Finally, we have the graph of the volumetric efficiency versus pump head for the 5 different viscosities tested. For all dilutions except for 54.1 weight percent glycerol, the volumetric efficiency decreases with increasing head. On the other hand, the 54.1 weight percent glycerol dilution has an increasing volumetric efficiency with increasing head. Since the gradation of the outlet beaker was 10 milliliters, the measured values had uncertainties of plus minus 5 milliliters, which is 40 to 50% of the total volume flow for some trials when the flow rate was measured. This factor could have skewed the volume measurements, resulting in volumetric efficiencies above 100%. Maximum efficiency points, at which operating conditions are usually chosen, occur at the lower pump heads.
While attempting this procedure, it is important to remember to measure the sample temperature before running it through the pump. The temperature can affect the viscosity of this glycerol solution. As well, you must ensure that the height of the outlet beaker is the same for each run. Minimize any spills that may occur by disconnecting and reconnecting components over the sample beaker. As well, remeasure the mass of the sample beaker before diluting it to take into account any sample loss that may occur during the final procedure. And finally, flush apparatus, clean a sample with water after each run.
Following this procedure, other methods like having a closed loop and an open loop to measure the head and the flow rate respectively can be performed in order to answer additional questions like the effects of hydrostatic pressure of the fluid in the inlet beaker on the experimental head.
After its development, this technique paved the way for researchers in the field of hemodialysis to explore the effects of blood properties on fluid pressures in the hemodialysis circuit and the effects of these pressures on physiology.